Lecture 7 is going to deal with, sort of, the causes of motion, the description of why motion occurs, how motion occurs. So far, we know how to describe motion. We've learned how to describe motion along a straight line with constant acceleration. Then we've looked at motion in 2 dimensions with constant acceleration, projectile motion. We've looked at motion in a circle. But we haven't asked the question, what causes motion? So that might seem like the logical next question. It isn't. The reason it isn't is because it's the wrong question about motion, and to understand motion involves not asking what causes motion, but asking another question. But before we go to that other question, we have to look at Aristotle, the Greek philosopher-scientist, who actually answered the question, what causes motion? And he did so more than 2,000 years ago, and because of that, we spent almost 2,000 years with the wrong question and the wrong answer. And I'm going to get you to understand why that's the wrong question and why that's the wrong answer. So what did Aristotle say? Well, Aristotle said, what causes motion? Well, pushing or pulling something causes motion. And that's pretty obvious to us. The name for a push or a pull is a force. So Aristotle said forces cause motion. And here are some examples from Aristotle's time. You have an ox cart. Well, how do you move it? You hook up the ox to it, and the ox exerts a force and pulls it. Or a chariot. The horse hooks up to the chariot, and the chariot gets pulled. And if the horse stops or the ox stops, the object stops. Here's a more modern example. Here's a chair. It's on wheels. Give the chair a push, force, it stops. Force causes motion. It seems to make a lot of sense. Push the chair, moves. Stop pushing, the chair stops. Push the chair, moves. Stop pushing, it stops. So Aristotle's idea seems to make a lot of sense. Plenty of other modern examples. You're driving a car, you take your foot off the gas pedal, pretty soon the car comes to a stop. You're pulling luggage through the airport, you stop pulling on the handle, the luggage doesn't keep going on its own. You walk, and you stop exerting forces against the floor, and you stop. So this seems to make a lot of sense. Now, there are some other areas of motion that are a little harder to explain with Aristotle's idea. For example, in his day, people used arrows. You shoot an arrow through the air. What causes the arrow to keep moving after the force from the bow stops acting? Well, Aristotle kind of had a theory about that. He said air from the front of the arrow rushes in behind the arrow and pushes it and keeps it moving. So he had a theory for that still contained the idea that force, pushes or pulls, are what causes motion. If we wanted to do a mathematical description of motion in Aristotle's theory, we would say probably something like this. We would say the velocity of an object, the rate of change of its position, as we've seen before, is proportional to the push or pull. That is proportional to the force acting on it. But Aristotle's question is the wrong question, and his answer is the wrong answer, and probably the biggest misconception introductory physics students have is they are, in fact, Aristotelian in their thinking. Again, it's not surprising. The examples I gave from Aristotle's time, the example of the chair, the car, the walking, all these things lead us to believe we need to push and pull things to make them move, because that's the way the world seems to be to us. But let me focus now on 2 slightly different questions that will help us to see what the really right question is. So first, imagine a spacecraft on its way to Jupiter, and it's been launched from Earth, its rockets have fired with great force, it's been launched into a trajectory that takes it to Jupiter, and now it's simply coasting through space. And the question is, what keeps it moving? Why does it just keep on going? It isn't firing its rocket motor, it doesn't need a propulsive force. What keeps it moving? That's question 1. Question 2 is, here comes a baseball from the pitcher heading toward the batter. The batter swings, and suddenly the baseball is on its way to the outfield. Why did its motion change? So 2 questions. One about the spacecraft coasting effortlessly through interplanetary space. The other one about the baseball that was coming from the pitcher and suddenly is on its way to the outfield. Why did its motion change? Question 1, the question about the spacecraft, the question that says, why is this spacecraft moving? What keeps it moving? That's the Aristotelian question, and that's the wrong question. The study of motion, Newton's whole theory of motion, is not about what causes motion. It's about the second question. It's about what caused the baseball's motion to change. Something did, and that something was the swing of the bat, and the bat colliding with the baseball, and a lot of physics going on there, but it was the forces exerted by the bat that caused the baseball to change its motion. Part of my goal in this course, and my goal certainly when I teach introductory physics to my students, is to get people to stop being, quote, closet Aristotelians. It's not surprising that we think in the Aristotelian mode, because we tend to experience the fact that to keep things moving, we think we need to push on them. And we're getting a wrong idea there. The right question, the question we really want to ask about motion is, what causes motion to change? Now, the first person to really get a hint of how motion changed and why change was important in motion was Galileo. Galileo actually did a number of real experiments. He also did what were called thought experiments, and he came up with a big idea, very big idea, the idea of inertia and the law of inertia. And I want to give you first in a visual and second in an actual experiment what the thinking was that led Galileo to this revolutionary new idea that changed all our thinking about motion. So Galileo did what's called a thought experiment. Thought experiments are very famous in physics. They're experiments that you don't actually carry out in the laboratory, although we will carry this one out here in just a moment. Thought experiments are things you think about what would happen if. And there are a great many famous thought experiments in physics, all the way from Galileo to Einstein and beyond, and they've led to very powerful insights, even though nobody did an actual experiment. So Galileo's thought experiment was this. He said, what if I take a ball and I roll it down some kind of trough-shaped track? And he had enough intuition to recognize that the ball would rise on the opposite side of the track to approximately the same height it started from. Galileo didn't know it at the time, but his insight there was a brief understanding of the idea of energy conservation, an idea we'll develop in a few lectures, and we'll develop rigorously using mathematics. And then Galileo said, well, what would happen if I took this ramp and made it more gradual on the far side? Well, he said, the ball should still rise to about the same height, which means it would travel further. And then Galileo's big insight is, what if I made the far side of the track completely flat? Well, the ball never has the opportunity to rise back up to its starting height, so it ought to just keep rolling forever along that flat horizontal surface. And Galileo concluded from that the natural state for things to be in was a state of motion, uniform motion, moving at constant speed in a straight line. And he formulated the law of inertia, which is attributable to both really Galileo and Newton. It's really Newton's first law, but Galileo was the first to state it in some form. And it states something like this. A body that's in uniform motion remains in motion, and a body that's at rest, which is just a special state of uniform motion in which your velocity is zero, remains at rest unless they're acted on by a non-zero net force. So the big idea here in the law of inertia is it's natural to be moving. You don't need to answer the question, why is something moving? Why is that spacecraft in motion? What's keeping it moving? Meaningless question. The laws of physics, as they pertain to motion, are about changes in motion, not about motion itself. Absent any forces acting on an object, it will remain in a state of uniform motion. And I want to emphasize what uniform motion means. Uniform motion means straight line motion with constant speed. No change in velocity, no acceleration. A change in direction or a change in speed, and you're not undergoing uniform motion. But in the absence of forces, net forces, and I'll describe that concept in just a moment, in the absence of forces acting on body, it remains in uniform motion. And so with this law of inertia, Galileo has transformed the dialogue about motion from the question, what causes things to be moving, to what causes their motion to change. So that's the right question. What causes motion to change? And the answer is the same answer Aristotle gave to what makes things move, but now it's what makes motion change, and the answer is force. It's not that motion itself requires force, but that change in motion requires force. And that's really the single most important thing to understand in mechanics. And let me give you a more sophisticated question. I'm not going to answer it right now, although we'll get to it in a few lectures. Question is, what keeps a satellite from falling down? Now, that sounds like a very logical question. You might ask that question. Somebody might ask it of you. You've taken a physics course. Tell me what keeps a satellite up. Well, that's the wrong question also. To ask that question is to think that a satellite should move in the direction of the force on it. And that's to think like an Aristotelian, to say force causes motion. But that's not what the satellite does. The satellite's motion is changing. It's not straight line motion. If it's in a circular orbit, it's a circle. And the motion is indeed changing in the direction of the force, which is toward the center of the Earth. And we can deal with the mathematical details of just how you get a satellite into circular orbit, and we'll do that in later lectures. But the point is, even that question, that seems like a very logical question to ask of a physicist, what keeps a satellite from falling, that's an Aristotelian question. That's the wrong question. And to ask that question is to presuppose that things ought to move in the direction of the forces that act on them. And that's the Aristotelian idea that force causes motion. But it doesn't. It causes changes in motion. Let's, before we move on to Newton, let's pause and do an experiment that actually verifies this idea of the law of inertia that Galileo came up with. So over here I have a modern-day version of Galileo's tracks. It's a nice flexible track. I have a low-friction car that rides on it, and I have the track configured right now in this bowl-shaped configuration. And of course, the real world is not perfect in the way that the world of thought experiments is, so nothing is perfect. It's not going to rise to exactly the same height it started from. But when I get this car on the track and I release it, it goes back up to almost the same height it started from. Eventually, something, friction in fact, slows it down and it comes to a halt. But there it is. There's Galileo's experiment in the first configuration of his track, in which it's a symmetric bowl-shaped thing where the object that rolls down one side rises to essentially the same height it started with until friction begins to act and do away with that. Okay, let's pause a moment and reconfigure this track into Galileo's second thought experiment configuration. Okay, here we are with the track in what's more or less Galileo's second configuration, the steep drop at first and then the gradual rise upward, Galileo's reasoning being that, well, now the car ought to go farther because it's going to try to get to the same height. So let's do the experiment. There it goes, and it rises to almost the same height it started from. Again, almost, because this is the real world and friction is eventually taking away some of its energy. We'll get into that in more detail later. But at first, at least, it rose to almost the same height it started from, and there it goes. So that's Galileo's second configuration. The car moved further this time because the track extended longer, the important thing being it rose back up to the same height. Now let's pause and reconfigure the track to Galileo's third and most insightful configuration. Okay, here we are in the last of Galileo's configurations. The track starts out again with a steep drop, but then it levels off and extends, in principle, horizontally forever. And what happens if we release the car? Well, what happens is the car cannot rise back up to its starting height because the track never goes back up again. And so Galileo reasons it should go forever. And there it is, trundling away. And when you come to the end of this 60 lecture course, it will still be moving at constant speed in a straight line, according to Galileo and the law of inertia. That uniform motion is the natural state of motion, that there is no explanation needed for something moving in a straight line at constant speed. Well, Galileo's work sets the stage for Newton. Isaac Newton, probably the most famous scientist of all time. Newton was born in 1642, which in the old calendar was the year of Galileo's death. By the Gregorian calendar, it was 1643 that Newton was born. And he was an interesting character. He was born in Woolsthorpe in England. He was a premature baby. It was said that he could fit into a quart jug. And in 1661, he headed off to Cambridge on a work-study program. And he studied at Cambridge University until 1665, when the plague shut down the universities, and he spent 2 years at home in Woolsthorpe. And those 2 years were extraordinarily productive for Isaac Newton. He worked on calculus. He was one of two co-developers of the branch of mathematics called calculus, and he had a good reason to develop calculus because he needed it to use his equations of motion to solve for the motions of the planets. He worked also on optics, and he developed his theory of gravity, which we'll look at in some detail shortly. He later, in his later years, became a member of Parliament, and he was the warden of the Royal Mint. So he had quite a varied career, Newton did. And what Newton did was to take Galileo's idea of inertia, the idea that an object remained in motion unless acted on by an external force, and he ran with that, and he used it to formulate 3 laws of motion. Newton's laws, very famous laws that describe motion in the Newtonian universe. And there are 3 of them. The first one simply restates the law of inertia. The second one quantifies the law of inertia, essentially, tells you how force and change in motion are related. And the third one, the famous, quote, equal and opposite reaction law, turns out to be necessary for a completely, fully consistent description of motion. And I'm going to devote an entire lecture to the third law because it's very much misunderstood, and it's also very important in understanding the physics of more complicated systems, particularly. So let's take a look at Newton's laws of motion. In particular, I'm going to look at the second law in detail because the second law subsumes the first law. The second law talks quantitatively about how motion changes in response to forces. The first law, remember, is the law of inertia. As Galileo stated it, no force, no change. Well, that's a special case of the second law. It says if there's zero force, then there's zero change in motion. The second law subsumes the first. So I'm going to focus on the second law. And the second law is at the heart of solving many, many, many of the real-world problems that arise in mechanics, in mechanical systems, in motion, and are used today, even though they were formulated hundreds of years ago, are used today by engineers and many others to formulate structures, to design cars, to do all kinds of things that we do. The second law is at the heart of that. So the first thing Newton needed to do when he developed his law of motion, his second law of motion, was to quantify motion. What is motion? How do I measure it? How do I quantify it? What's the, quote, quantity of motion is the term Newton used. And he came up with this quantity, the product of the object's mass, and we'll talk a little bit later about exactly what mass means, but the product of the object's mass with its velocity. That product is called momentum. Momentum is m times v, mass times velocity. And for Newton, that was the quantity of motion. And you can see that kind of makes sense. Stand by a highway and watch a big truck go by or a small car go by. Even though they're going at the same speed, there's something more there in the motion of the truck. In fact, there's two things more, as we'll soon see. One of them is momentum. Another, as we'll get to in another lecture, is energy. But that's getting ahead of things. The quantity of motion for Newton was momentum, the product of mass and velocity. And Newton said, I think the rate of change of this quantity of motion is equal to the net force that's acting on the object. So Newton's law is really a statement about momentum and changes in momentum, where momentum, the product of the mass and the velocity of an object, is a measure of its, quote, quantity of motion. Now, when the mass doesn't change, so that the mass is constant, then the rate of change of the momentum reduces to the mass times the rate of change of the velocity. The momentum is the mass times the velocity. The force acting, according to Newton's second law, the net force acting, is the rate of change of the momentum, the rate of change of mass times velocity. But if mass is constant, that becomes mass times the rate of change of velocity. And we know what the rate of change of velocity is. It's acceleration. So Newton's law in the case of constant mass reduces to the formula that's widely known, F equals ma, force equals mass times acceleration. That's a restatement of Newton's original idea. The quantity of motion changes in proportion to the force. Now it's the acceleration of the object is in proportion to the force, and here the proportionality is the mass of the object. That's what F equals ma means. So let's take a look at Newton's first and second laws. The first law, again, simply restates the law of inertia. It says an object in uniform motion remains in motion, and an object at rest remains at rest unless acted on by a non-zero net force. It's subsumed by the second law that says the rate of change of an object's velocity is proportional to the net force and inversely proportional to its mass. And there I've written the equation F net, and I want to emphasize net, and I'll say more about that in a moment, equals mass times acceleration. You'll notice also that I've been careful to put the arrows over both the force and the acceleration because both of these are vector quantities. We've already seen that acceleration has a direction, which need not be the same as the direction of the velocity, by the way. And force, being a push or a pull, definitely has a direction. It matters whether I push you this way or that way. So both of these are vector quantities, and Newton's second law is a vector statement about the relationship between force and acceleration. The second law also helps us to define the units we use for forces. The unit of force is the Newton. And incidentally, there's a convention here. When we name a unit in physics after a person, the convention is that we write the unit with a lowercase letter, but we write the symbol for it, in this case, capital N, in capital. So if you see units like the joule for James Joule or the Newton for Isaac Newton, you'll see them written out in lowercase. That's not a mistake. But when the symbol is just used, then that's in uppercase. So let's think about units of force for a moment. Newton's second law says F net is ma. F equals ma. That defines a force unit. The force unit is the Newton, symbol capital N. It's the unit in the system international, the international system of units. And the Newton is defined such that if a 1 kilogram mass undergoes an acceleration of 1 meter per second, that is 1 meter per second squared, then the net force acting on it is by definition of 1 Newton. So first of all, Newton's second law serves to define units of force. The English unit, by the way, is one that's familiar to you. It's the pound. And a pound is a unit of force, and a pound is about 4.5 newtons, roughly 4.45 newtons. So those are units of force. Let's take a closer look at Newton 2, because Newton's second law is something that is widely misunderstood, and students get quite confused about it. So here's Newton's second law again. F net, the net force, is equal to the mass times the acceleration. What F net is the net force. It's the sum, the vector sum, of all the different forces that may be acting on an object. And those are real physical forces, pushes and pulls, like me pushing with my hand, or a spring being stretched, or gravity, or a magnetic force, or something like that. They're real physical forces. The right-hand side of Newton's law is the product of the object's mass with its acceleration. It's a vector quantity too. Mass is a scalar, no direction, but acceleration is a vector, so this is a vector quantity. And the equal sign indicates that these two things are mathematically equal. But it doesn't mean that they're the same things physically. And a great big common misconception is to think that the right-hand side is another kind of special physical force and make up silly names for it and all kinds of other things. It isn't a force. It's simply the product of the mass and the acceleration. All the real physical forces are on the left-hand side of Newton's law. And to understand and use Newton's second law, you've got to appreciate that distinction. The equality means they're mathematically equal, but it doesn't mean they are physically the same thing. Let's talk a little bit about the net force. The net force is the vector sum of all the physical forces that are acting on an object. So let's take a look on the big screen here at the net force. So here's an object subject to a single force. In this case, that force F is the net force on the object. On the other hand, there might be two physical forces acting on the object. In this case, we have two forces. I've labeled them F1 and F2. And because they point in the same direction, their vector sum, the net force, is simply a vector twice as long as either of them. So there's the net force in the case where two physical forces, F1 and F2, are acting on the same object. On the other hand, the two forces might act in opposite directions. So F1 is pulling to the left, F2 is pulling to the right. They're the same length, indicating the forces have the same magnitude, and so they sum up to zero net force. So even though there are two forces acting on this object, it's as if there were no forces acting. As far as Newton's second law is concerned, there is no net force on the object, and its motion will not change. And that's an important concept. Just because you see a force acting on an object doesn't mean its motion is going to be changing. There may be other forces that cancel that force and make zero net force. On the other hand, we might have a situation where there are a couple of forces acting in different directions. So here's force 1 acting to the right, force 2 acting down. Again, the net force is the vector sum of those two, and we know how to form those vector sums. We form them by going along one vector and then going along the other vector and forming the resultant vector between the two of them. So there is F net in this case. It's a force that is larger than either one, but not twice as large. In fact, if you want to get mathematical, it's the square root of 2 times as long as either one. And it's pointing diagonally downward at 45 degrees because F1 and F2 had the same magnitude. So the net force is what's important. The net force is always what enters Newton's law. Now, what are some forces? Let's look at some examples of forces. There are familiar forces. There are pushes and pulls. Oh, I push on this table. That's a push. I pull on the table. That's a pull. What are some other forces? Well, there are forces associated with common objects like springs and this bungee cord. If I pull on the bungee cord is exerting forces now on both my hands. My hands, by the way, are exerting forces on the bungee cord too. Here's a spring. I can stretch the spring. If I do that, the spring is exerting forces that are pulling back on both my hands, or I can compress the spring, in which case the spring is pushing out on both my hands because it wants to expand. Here's a piece of rubber laboratory tubing. Stretch it. There's a lot of force, tension. It's called a tension force in this case. When I pushed on the spring, it was called a compression force. So those are some common everyday forces. Another important kind of force is called a normal force. And to get at the normal force, let me ask the following simple question. Why don't I, standing here, fall through the floor? After all, gravity is pulling down on me. If I were not on the floor, I would be falling because of gravity. But why am I not falling through the floor? Well, it must be that there's no net force on me. I'm not accelerating right now, and so Newton's second law says F must be 0 if A is 0. Well, F is 0 because there's a force pushing up on me from the floor. And that force forms quite naturally when I stand on the floor. I begin to try to sink into the floor, but quickly forces develop in the floor. They're essentially electrical forces associated with the atoms and molecules, the interactions between the atoms and molecules in the floor, and very quickly they conspire to exert an upward force on me exactly equal to the downward force I'm exerting, and there's no net force on me anymore. The details, the electrical details of how that happens are complicated, but it does happen, and I end up being supported by that so-called normal force. It's called a normal force because it's at right angles to the surface I'm in contact with, in this case, the horizontal floor. So those are some familiar everyday kinds of forces. What are some other kinds of forces? Well, some other kinds of forces are invisible. Some of them are also everyday and commonplace. Perhaps the most obvious one is gravity. Gravity, again, is a force that acts on all objects toward the center of the Earth, at least here near the surface of the Earth. We'll see more about gravity in a later lecture. So if I take this block and I drop it, down it goes until it hits the floor, and now some normal forces are acting on it to keep it from falling any further. But during the time it was falling, the force acting was everyday, common variety gravity. By the way, the force we know least about in the whole universe. Nevertheless, a very common force to us. Another force, and I'll use the same block for my example, that's an invisible force is the force of friction. I push the block, and like the chair I was pushing earlier, or Aristotle's chariot, as soon as I stop pushing, it stops. Why? Because there's another force acting that I don't see, and that force is the force of friction. Another example of an invisible force is the electromagnetic force, or the electric and magnetic forces. They'll turn out, as we'll see in section 4 of this course, to be manifestations ultimately of the same thing. Here are a couple of magnets. Their north poles marked in red, and I can't push them together. There's an invisible force trying to repel them. It's very hard. Flip them around, there's an invisible force pulling them together, and there they go, and it's hard to pull them apart. That's an invisible force. So plenty of forces are invisible. We don't see them, and that's another reason why we tend to be closet Aristotelians. We don't see friction, and so we think it takes a force to push on this block. But actually, if I push on this block and it's moving at constant speed, Newton's second law tells me the net force on it is, in fact, 0. Well, let me end by looking at the most fundamental forces there are. Physicists have identified 3 fundamental forces in the universe. We think sometime we will understand them as all aspects of one common force, but we simply aren't there yet. So here's a look at the fundamental forces of nature as we now understand them. We have an example of how some of these forces have come together over time. For example, at the top we see electricity and then magnetism. They merged in the 1800s. We came to understand them as aspects of the same thing called electromagnetism. In the later half of the 20th century, we understood a rather obscure force called the weak nuclear force that has to do with a certain kind of radioactive decay as being another aspect of the same fundamental force that included electromagnetism, and that became the electroweak force. We generally think of those two things as separate, and you'll hear some physicists say there are 4 fundamental forces, but we really understand the weak force and electromagnetism as the same. There's the strong force, which binds particles together, binds quarks together to make atomic nuclei, binds atomic nucleons, protons and neutrons, and binds the neutrons and protons together to make nuclei, the strong nuclear force. We think we see probably how to merge the strong and electroweak forces, but we aren't there yet. The result would be called a grand unified force. And the force that we understand least is the force of gravity, and we don't really see yet how to combine it with the other forces and understand that. But if we did, we'd have what some physicists call a theory of everything. But the point I want to make for the purposes of this lecture is that these fundamental forces are really all nature has to work with. They are the things that ultimately change motion. You may say, well, what about all those forces in the springs and the magnet is an example of electromagnetism, but the forces of the springs, the normal force of the floor, almost all the forces, the pushes and pulls in my muscles that we encounter in everyday life are in fact ultimately electrical forces involving interactions between electrical charges in the matter that makes us up. The other force that's very common, of course, is gravity, that one we really don't understand very well. So let me summarize. The way forces change motion is fully described by Newton's laws. The first law, an object in uniform motion remains in motion, and an object at rest remains at rest unless acted on by a non-zero net force. The second law talks about the rate of change of an object's velocity, its acceleration being proportional to the net force and inversely proportional to its mass. F net, the vector net force, is mass times the vector acceleration. And finally, the third law, the action and reaction law, that will be the subject of Lecture 9. But before we get to Lecture 9, we'll look at how we use Newton's laws in particular cases.